Okay. Okay, let's see.
Inner matrix that we have to do.
Hi. Now this section is about linked lists. So in this video, we will learn why we need linked list. So for covering the topic, I'll be discussing about these two things: problems with arrays and the difference between array and linked list. So first thing, problem with an array. Array is of a fixed size. Whenever you are creating an array, you have to mention the size, and later on you cannot increase or decrease the size of an array.
Fucking bitch. So we have a list of things. We have a previous pointer. No, a previous pointer, a current pointer, and a temporary pointer. And what is happening is, let's take another color. Current next, so this is temporary. Current next, so this is equal to previous, and previous is equal to, so current next is equal to previous. Okay, this value, right? We're switching the value. So why weren't you using the thing called value in itself? So this element is not, it's not a traditional array. That's what we gotta remember. So this points to here, this points to here, this points to here, this points to here, this points to here. Okay, and we have fucking bitch. This will be the current, previous would be nothing, and temporary would be this thing, right? And we are kind of decoupling. So what happens is, when temporary is current dot next, okay, when current dot next, when this thing becomes previous, it kind of goes here, right? And current dot previous is equal to current. So this happens, right? And current is equal to temporary. And this gets restarted again. Temporary. So the loop starts back again. Temporary is equal to current dot next. Okay, this happened. Current dot next. Current dot next is equal to previous. Previous is equal to current. Okay, no. Current dot temporary. Current is equal to temporary. Previous is equal to current. Is equal to current, meaning this goes one step here, and that current is equal to temporary. This one moves one step there. Current dot next. Current dot next. And current dot next is previous. This goes to here. And current is equal to temp. Back again. I can kind of get what's happening, but let's try it. While current is true, okay, while current is true, temp is equal to temp temp is equal to current dot next always. Okay, current dot next be previous, will be none. Okay, this will break the thing. This breaks the bond, and previous will be in the spot of current. Current will be in the spot of temp. This will this will point backwards every time. It points backwards because this thing will help it point backwards. At first it points it to nothing, and second iteration it will point backward. That's what's happening, and I need to return Okay. Okay. Previous. Is recursion similar to mm, 2846? What the fuck? You're given a head of a slightly linked list. The position of the linked list is 7. What? The position of the linked list of length of 7 can be initially represented as 1, 2, 3, 4, 5, 6. Reorder node will be the following order. So 0, 6, 1, 5, 4. Okay, what the fuck is going on? Notice that the general case of the linked list n is equal, length is equal to n. The nodes are reordered to be the following order. What the hell? So, oh, okay, -1. Cool. Can it not be done? Length of head and how do you, oh, you just point them, point. You need to point all of them, point. reorder the nodes from the following order. N minus 1, 7. Oh, how do I do that though? I need to do, how do I know it's 0? 0, n minus 1, n minus 2, 2. Like, what? What? Like, okay, give me a hint. A brute force solution will restore more nodes in an array, reorder the value, create a new list. Can you think of a better way? Perhaps try reordering the node directly in the place, or adding an extra step. I in range, holy shit. Range in okay, what is happening? How do I reorder this shit? I don't get it.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem reorder list. So we haven't done a linked list problem in a while, and this is a pretty common and interesting linked list problem. So we are given the head of a singly linked list, where we have the first value, the next value, etc., and we want to rearrange it into this order. And a better example would be, so for example, take this linked list, and we have 1, 2, 3, 4. That's a straightforward ordering, but we want to take the first value, leave it here, then take the last value, move it in the second position, then the second value gets pushed forward, and then the third value is going to go next. And so in other words, what we want to do is, given the original list, we want to take, the first value, put it in the first position, then take the last value, put it in the next position, then take another value from the beginning of the list, put it in the next position, then take another value from the end of a list, and keep doing that. So basically, we're alternating between the beginning and the end, and we're continuing to pick nodes, and then building a new linked list. So just like the problem name, we're just reordering this list. We're not actually going to be creating new nodes. We just want to take each node and then put it in the correct position in the output string, and then we don't have to return anything because we're just modifying this list in place. So there are many ways to do this problem. I'm going to be focusing on the solution that we can do in linear time. Basically, n is the size of the linked list, but we're going to do this without any extra space. And it's not too difficult to do this with extra space, but without extra space, it's a little bit more tricky, but it's also pretty doable. So that's what I'm going to be focusing on. So if we were using extra space, what we actually could do is take this entire thing and put it in an array. So each node goes in the array, and what we would do is we would take the first portion, leave it as it is, and then we would take the second portion and either reverse this entire portion or just go through it in reverse order. So, something like this, having one pointer at the beginning, one pointer at the end, and using that we would build the output list where we would say, okay, the first pointer is, the first position, the second pointer is going to be the next position, shift the pointers by 1, and basically rinse and repeat until we've done the entire list, right? Take this, put it in the next position, take this, put it in the next position, and then, if we had an array with each value in the correct position, for example, if we built an array that looked exactly like this, then of course we could take the nodes themselves and create a linked list following that exact same ordering. But we can actually do this without using an array. We can do this without using extra memory, so let me show you how to do that. So the idea is going to follow similar to what I just showed you. We want to take the beginning of the list and merge it with the second half of the list, right? So this is the first half, this is the second half. We want to merge these together with alternating values, right? So this is going to go first, and then this is going to go second. So obviously, we're not merging them from the beginning. The second list is going to be merged from the end. But if we're not putting this in an array, how exactly can we do that? Because we're going to have one pointer at the beginning of the first array. We're going to have one pointer at the end of the second. I think I said array, but what I meant is list. Obviously, we're going to have two lists. And so the first half of the list is going to be straightforward, right? We're going to take, this is going to be the node that goes at the beginning. Then we're going to take this pointer, shift it to the right. So that's pretty straightforward. But since we have a pointer at the end of the second list, and we take this node and we put it in the second position, right? We'll insert it somewhere in the middle over here. That's not impossible, right? We can do that pretty easily. But the problem becomes, okay, once we've inserted this node, then we want to move our pointer to this node, but the link is going the wrong way. The link is going in order, but we really want the links to be going in the opposite order, because when we traverse this second portion of the list, we're not going to be going from beginning to end. We're going to be going from end to beginning. So how can we do that without extra memory? Well, the easy way is, why not just reverse the links, right? For this entire second second portion of the list, why don't we reverse every single link, and then we can do it pretty easily, right? There's no reason that we can't reverse the link. We're perfectly free to do that, so that's kind of what makes this problem a lot easier. There's going to be two phases to this algorithm mainly. We're going to take the second portion of the list, reverse it, and then we're going to take these two portions of the list and merge them together. This first, next to this value, then this, right, et cetera, et cetera. The only other things I want to mention is when we're reversing the second half of the list, how do we know what is the second half? How do we know we've reached the second half, right? Starting from here is when we want to start reversing. How do we know once we get there? You can do it multiple ways. The easiest way is going to be a fast and slow pointer. So I'm going to have the slow pointer initially at the first and the fast pointer initially at the second node. We're going to be shifting the slow pointer by 1. We're going to be shifting the fast pointer by 2. And we're going to keep going until the fast pointer either reaches the end of the list or reaches the last value of the list. And once that is the case, we know that the slow pointer is going to be, if it's an even list, you can kind of run through it yourself and see that it does work. But if it's an even list, the slow pointer will be at the halfway point, pretty much, right? It'll be at the end of the first list, right? So then what we'll do is say, okay, slow next is going to be the beginning of the second half of the list. So that's what happens if we have an even number of nodes. What happens if we had a odd number of nodes? Let's see if the same thing works out for us. So if we have a slow pointer here and a fast pointer here, we'll shift the fast pointer by 2. It will be over here. The slow pointer will be over here. Then we'll shift the fast pointer by 2 again, so it'll be at null over here. The slow pointer will be at this node. So I guess the question becomes, what in this case, what's the second half of the list? Because obviously we have an odd number of nodes. Well, what we're going to say is this is going to be the second half of the list. Even though it's shorter than the first half of the list, it still works for us, because what the result in this case is going to be is basically, we have this second half of the list. This is the first half. We're going to take 1 at the beginning. We're going to take 5 in the next position. Then we're going to take 2 in the next position, right? We're just basically alternating. Then we're going to take 4 at the next position, and lastly we're going to take 3 in the next position. So it does work out in this case. So you can see that finding the middle of the list is something that can be done with 2 pointers, one fast and one slow. And in terms of actually taking these lists and merging them, it's pretty straightforward when you look at the picture. Actually coding it is a little bit tricky because we're going to have several different pointers, but just to give kind of the rough idea, we're obviously going to have a pointer here, which is going to be the beginning of the first list. We're going to have a pointer here, which is we're going to call the second pointer, the beginning of the second list. Obviously the link here is going to be going the other way. What we're going to do is we're going to take, okay, this pointer dot next, right? 1 dot next is, instead of being set to this node, we're going to break this link, set it equal to the second node, which is 5, and then of course 5 is pointing at this node 4. So instead of having it point at 4, we want it to be pointing at this node, which was the original next node 1. So we're going to do that. 5 is going to point at the second node, and then we're going to shift our pointers. We're going to take this pointer, set it to 2, take this pointer, set it to 4. Now obviously notice how we broke the link in both spots. So how are we actually going to be able to shift the pointers if we broke the link already? Well, we're going to have to save that link before we actually break it. We're basically going to have a temporary variable which is going to point at this node and a temporary variable that's this node before we actually break these links. I think that'll make more sense when we actually code it up, but that's basically the idea. And obviously these 2 pointers, we're going to keep shifting them until they basically meet each other. And actually one last thing, notice how the first list, so when we actually cut this in half, once we actually have a first half and a second half of the list, for the last node in the first half of the list, we actually want it not to be pointing at 4, but since this is going to be the last node, we want this to be pointing at null. So that's one other thing that we're going to do. So obviously this is kind of about all the edge cases and making sure all of our pointer manipulation is going well, but once you have that down, you kind of have this main idea down, coding up isn't too difficult. That being said, we can jump into the code now. Okay, so now let's dive into the code. You can see we don't have to return anything, we just have to modify the list in place, so that's what we're going to do. And remember, the first thing we want to do is find the actual middle point of this list. So we're going to have 2 pointers, slow and fast. Slow is going to be at the head of the list, and fast is going to be head.next. We're going to keep going. We get null, fast is non-null, and fast has not reached the end of the entire list. And as that's the case, we're going to basically shift each pointer. Slow is going to be shifted by 1. Fast is going to be shifted by 2. Okay, so that's great. So now we do have the beginning of the second half of the list. So we're going to have that second pointer. And remember, just like in the drawing picture, the beginning of the second half of the list is going to be the slow.next. So this is the second half of the list. But remember, now we actually have to reverse the second half of the list. Before I reverse it, I'm also going to say slow.next is going to be set to null, right? Because we're actually splitting this into 2 different lists. So that's how we're splitting it. Now we're actually going to be reversing that second half of the list. So we're going to say while second is non-null, we want to set it to the previous node. Initially, the previous node is just going to be null, so we can set that as well. I think I can actually do it on this line. Previous is also going to be set to null along with slow.next. So basically, each iteration of the loop, we're going to store a temporary variable for second.next. But before we actually shift our pointer, we're going to say second.next is going to be equal to previous, which is initially going to be null. And then, of course, we're going to update our pointer. So now previous is going to be equal to second, and second is going to be shifted to our temp, which is going to be the next node in the list. So with this loop, all we're doing is reversing the second portion of the list. Okay, so now is the part that the second half has been reversed. Now we're actually going to merge the 2 halves of the list. So the beginning of the second, right? We want to find that beginning of the second, which is going to be the previous pointer actually, because remember, after this loop is done executing, second is going to be set to null, but previous is going to be set to whatever the last node that we looked at was, and whatever that last node is actually going to be the new head of the second half of the list, similar to what we had in the drawing picture. So that's the second half. The first half is just going to start at the head, right? So what we can say is first is going to initially be the head, second is going to be whatever happens.
Lead code 1. I think I can. Oh fuck! Did I?
Okay, let's solve leak code 33 search.
33. I haven't solved it. So you're given an array of length of n, which was originally sorted in an ascending order. It has now been rotated by which was originally sorted in ascending order. It has now been rotated between 1 and n times. For example, the array, if it is 4 times, okay. Yeah, this is some, we're taking some sort of graph, right? And we're taking some sort of graph and we're cutting it here, and we are like rearranging it so that it's so that it's here, right? Something like that. So that it's here this way. So that's what's happening. I don't know what it is called. So I think we should the way to approach this problem would be, you're given an array of n, and so let's say n of 4 times, right? So we have whatever, and we're cutting the number 4. Okay, so this array over here is gonna 1 2 3 4 5 6 3 4 5 6 will go what? So if this value is bigger than this value, we're just gonna put the last, wait, we're just gonna flip this, right? This is gonna get flipped. No, 1 2 3 4 5 6 4. That's one way to see it. So let's say this is 4, right? Fucking faggot. So let's say this is 4. I used to clean toilets. Let's go. I used to clean toilets. I used to like, fucking hell, let's go. I'm such a G. So boom, boom, boom. It's like so. This is the middle. If the number is bigger than middle, I just don't like this guy. Fucking up. Fucking unbearable piece of shit. If it is 1, 2, 3, 4. If it is bigger than middle, this switch needs to happen, I think. Okay. The first use case would be if target not in nums return -1, so that would be the first one. So this one is done. Now I just don't like seeing it. Not in nums return -1. Okay, that's one way to do it. So this needs to be in the first, and it's asking how many iterations it would take to get there. So let's visualize the graph in whatever way, and let's say okay, shit like that, right? And where is 1? So we are finding where the 1 is. If 1, the index of 1 is bigger than medium, so let's take the mid is going to be nums of, how do you find the mid? How do you find the mid? Okay, I need a length of n. Divided by 2. That will be your middle value though. N divided by 2. Okay. If your n is bigger than mid, nums of mid, I mean, what's the point? I could just do it here, nums better modality, bro. Okay, if that is bigger than mid, There needs to be different law. Okay. So we need to go to the right hand side and go and ask if it is in the middle. Back again. Is this a binary search or what? Oh, it is a binary search. I was thinking something else. Okay. If it is... Wow, great intuition. Okay. If it is not in the mid... Okay, I think I can do this. Okay, I need to do it in a loop. So while... while something, I don't know, while something is going on, while n, okay, no, while nums of mid, I don't know, okay, that is bigger. If it is not in the mid, it says here so I just need to find the location of it, right? Yeah, I just have to find the location and return. So if it's here, that's one rotation. Yeah, I just have to find the rotation. Okay, if oh, of course, binary search, left and right. Why did I blank out? This is supposed to be like an easy question too for me. And so if R is bigger than mid, okay, nums of mid. If R is bigger than nums of mid, if nums of big is bigger than the entire list, I mean, how can that be? So okay, if target is bigger than nums of mid, if target is bigger than nums of mid, what will be the right side? How do I
search and rotate and sorted array. So we're basically given an array that was originally sorted like this one, but then it became rotated like this one. And by rotated, they mean that they took a certain pivot or index of the array, like right over here, and then they cut it in half and then swapped the portion. Right? So you can basically think of this right-hand portion being swapped over to the left side over here. Right? That's what happened, as you can see here. Right, these two halves were put in the opposite position. And we're also given a target value in this example of target 0, and we want to check if our array contains this value. If it does, we return the index. If it doesn't, we return -1. The most straightforward way to approach this problem is literally just check every single value. Is our target? Is our target? Yeah, we get rid of our target, and then we return the index 4. Now this is just too trivial a solution, right? The time complexity is bad until it can, but can we do better? In this problem, they literally tell us to find a solution that's code log n, so obviously we can. And basically, anytime you're looking for a solution that's log n or better than linear, almost every time you're going to be looking for a binary search type solution. So since this array was originally rotated, can we use that to our advantage to potentially find a binary search type solution for the problem? Let's try to analyze it and see what we can find. So given that the original array was sorted, if you wanted to represent that as a graph, we would basically have a continuously increasing line. It might not necessarily be linear, but it's always increasing, right? And then we put chunks of it over here, and then swap these halves around, right? So let's draw what that would look like. So let's say the left side was exclusively greater than the right side, because that's what it means by rotating the array, right? So I think this is a pretty good way to visualize the problem to kind of understand what it would look like. And you can use this to your advantage to find potential patterns that can help us find a binary search solution. So with a problem like this, we really have to break it down into discrete cases and then use those cases to form a solution. So the most obvious thing is that there are two portions of the array, right? There's a left portion and a right portion. Both independently are sorted, right? So it's like we have two halves that are sorted. And so we know that a binary search usually has three pointers, a left pointer, a middle pointer, and a right pointer. The left is always going to be less than or equal to the right. This is just something you kind of know. From binary search. So let's say our middle value was 6 at some point, right? This means that we're in the left sorted portion of the array. So can we use that to our advantage? So let's say our target was greater than 6. In that case, we know for sure, since we're in the left sorted portion of the array, none of these values are greater than 6. So we can basically say these are eliminated. Let's run binary search on this portion now, right? So that's pretty easy. If we know that we're in the left sorted portion and our target is greater than the middle, this is what we can do. What if our target is less than the middle value? So what if our target was less than 6? Well, these two numbers are less than 6. And these three numbers are less than 6. So how do we know which way to go? Do we go left or do we go right? Because we can't go both directions in a binary search. The key is to see that in our left sorted portion, the smallest value is right here, right? Or on our graph, it's right here. So if our target is even smaller than this left value, 4, in that case, we know that we don't have to search 4, we don't have to search 5, we don't have to search 6. We can run binary search over here. But if our value is greater than or equal to 4, then that means we're going to run binary search on these two values, right? It's less than 6, but it's greater than the right sorted portion. Look at the code to better understand what these cases are going to look. So we're for the array -1 to the right, because imagine we're given an array like this, we're just check going to be left. And it's possible the case, then we need to check which portion of the array are we in. Are we in the left sorted portion? And like is greater than the left value, or greater than or equal, right? Because it's possible that the middle value and the left value could be the same value. The else condition would be that we're in the right sorted portion. So the simplest case is that our target is greater than the middle value. In that case, we're going to search right. So we can say our left pointer is now going to be middle, alt plus 1, and condense them. We can get rid of this and say instead if the target is greater than the middle, or if the target is less than the leftmost value, then we have to search the right portion. So we can get rid of this. And if this isn't true, that means the target is less than the middle, but it's greater than the left. That means we search the left portion, so we can update our right pointer. Type over here, we're not calling it left, we're just calling it L for short. And so this is if we were in the right sorted portion of the array. The easy thing is if target is less than the middle, that means we go left, so we can update our right pointer to mid -1. So if this isn't true, meaning target is greater than middle, and the target is greater than the rightmost value, that means we have to go left as well. So right equals mid minus 1. Notice again how these two are doing the exact same thing, so we can condense them. We can say at the top if the target is less than the middle, or if target is greater than the rightmost value, then we're going to search the left portion, so we update our right corner, so we get rid of this. And the else condition is that the target is greater than the middle value, and the target is less than the right value. In that case, we only have to search the right portion of the array. So we update our left corner to mid plus 1. These are all of the cases, right? So if we find our result, we're going to return it up here. But if we don't find it, we'll exit the loop and we'll return -1. And just as I expected, because I just finished the problem like a half hour ago, it worked perfectly. So this is not an easy problem. The code looks pretty easy, but you really have to understand the discrete cases. Like, are we in the left sorted portion or the right sorted portion? And then what's going to happen as a result? Which part of the array do we have to check? Okay, let's solve LeetCode 33 search and rotated sorted array. So we're basically given an array that was originally sorted like this one.
Hey guys. Greg here. Let's solve LeetCode 33, which is search in rotated sorted array. Now, firstly, if you haven't solved the problem find minimum in rotated sorted array, you should definitely do that first. I have a video on that. If you have, then here we are. So behind the scenes, imagine this array was actually sorted first. So it was 0, 1, 2, 4, 5, 6, 7. It's now been rotated, which means all the values have been shifted over, and if they ever go out of bounds, they go to the back here. So this array was actually rotated 1, 2, 3, 4 times. 0 should originally be at the beginning, so it's been rotated 4 times over to get to the right, and so it's now 4, 5, 6, 7, 0, 1, 2. So you can find the minimum value here with kind of a cluttered binary search, and that's covered in the other video, although we'll have to cover it a little bit again here. So you can find that minimum value here, and that was the solution or the end to the other problem. That's basically the beginning of this problem. After we've located this pivot index here, or the minimum, you actually have a target to find. So we are looking for the index of where 0 is, and if you can't find it, that's when you return -1. Okay, so let's solve the same example. These are the same numbers. So the first thing to do is to find that pivot index, or the value of the minimum. And we know that we can do that with a binary search. I'm not going to cover that, watch the previous video. And you will come up with a pivot index or a value of the min index, which I'm just going to call min index here. Okay, so that is going to equal, well, in this case, it's going to be 4. It's going to be where the minimum is. We run that algorithm, then here we are. So behind the scenes, imagine this array was actually sorted first. So it was 0, 1, 2, 4, 5, 6, 7. It's now been rotated, which means all the values have been shifted. Hey guys, Greg here. Let's solve LeetCode 33, which is search in rotated sorted array. Now, firstly, if you haven't solved the problem find minimum in rotated sorted array,
You given, bro. Just give me the solution.
You should definitely do that first, and I have a video on that. If you have, then here we are. So behind the scenes, imagine this array was actually sorted first. So it was 0, 1, 2, 4, 5, 6, 7. It's now been rotated, which means all the values have been shifted over, and if they ever go out of bounds, they go to the back here. So this array was actually rotated 1, 2, 3, 4 times. 0 should originally be at the beginning, so it's been rotated 4 times over to get to the right, and so it's now 4, 5, 6, 7, 0, 1, 2. So you can find the minimum value here with kind of a quarter binary search, and that's covered in the other video. I'll cover it a little bit again here. You can find that minimum value here, and that was the solution or the end to the other problem. That's basically the beginning of this problem. After we've located this pivot index here, or the minimum, you actually have a target to find. So we are looking for the index of where 0 is, and if you can't find it, that's when you return -1. Okay, so let's solve the same example. These are the same numbers. So the first thing to do is to find that pivot index, or the value of the minimum. And we know that we can do that with a binary search. I'm not going to cover that. Watch the previous video. And you will come up with a pivot index, or a value of the min index, which I'm just going to call min index here. Okay, so that is going to equal, well, in this case, it's going to be 4. It's going to be where the minimum is. We run that algorithm to find that minimum index. We require that. Now, after you have that min index, we have a partition where we have everything to the left is this increasing range, and you have everything inclusive, and to the right is another range. If our targets, for this example, let's say we're looking for 5, well, we need to look in this range, which means that we want L to be 0, the first index, and we want R to be, what is this? Well, that's basically the min index -1. So we want L, and we'll say the condition to get there in a second. We want L and R to equal 0, and I'm just going to call the min index M, so I'm just going to make it simple here. This is the min index, which is going to be located here, not the middle, is the min index. We want L as 0 and R as M -1. We're searching for 5, and we end up in this range because 5 is at least the first value, and it's at most the value that's the maximum, or equivalently 1 less than the minimum. So we want to run this situation only in the case where T is at least our nums at 0, so it's at least the first value, and it's true, it's got to be at most the nums at M -1, and T has got to be at most nums at M -1, our min index -1, equivalently our maximum value. Okay, so that is our first situation. That's when we end up on the left bounds is following that rule. Okay, but now let's say our target was actually 0. Okay, and it could have been 0 or 1 or 2, all those work. So in this situation, we want L and R to equal M. It could be inclusive in the min as well. So we want to start at M, and we want to go at most to the very end, which is actually index M -1. So we want to start L at M and R to N -1 in the situation of what? Now you could just say this is an else here. Okay, that kind of works. Except the problem with this is that there's actually more than 2 situations. Why is that true? Well, here it only looks like there's 2 situations because there's basically this big left partition and this big right partition. Boom, I just created a valid situation where there is no 2 partitions here. There's really only just the 1 partition. It's the original sorting. But the minimums at the beginning, the maximums at the end, and they're all just increasing in order. There's no 2 partitions. These 2 situations work for every situation that's not this one. So really, I'm just going to count this as kind of edge case here. Our target doesn't really matter what it is in this case because this is perfect range for binary search. We can just search for any value here. And so we want L and R to be traditional binary search. So L is going to be 0 and R is going to be the last index N -1. In the case that is particularly this, which is that the min index, which we're again calling M here, where the min index is equal to 0. Okay, that's the only situation where this comes up is if your min index is 0, that automatically implies that it's sorted like this, and therefore this is our third kind of edge case situation. Traditional binary search. Okay, so let's write our code. Now the first step is going to be exactly the same as just find minimum and rotated sorted array. That's going to be one binary search. So we'll get N is equal to the length of the numbers array. We are going to start L equal to 0 and R equal to N -1, and then we'll run while L is less than R because we want to escape from them equal to each other. Then we'll have that L and R both fall on the minimum index. We get M is equal to L plus R over 2 index. If nums at M is greater than nums at R, that actually means that the min index is strictly to the right side. We want L is equal to M +1. Then otherwise, if that's not true, well then M actually could be the min index. So we want to keep that. We set R equal to M. At the end of this, we'll get our min index is either L or R, and so we'll just store that the min index, which I'm calling min I, that is equal to L, or R would also work. Now we need to do another binary search, knowing that we have this spot where it fits. So we need to set up our bounds for our binary search, which is again just going to overwrite our L and R. If it's true that the min index is equal to 0, that is the edge case where we just want to run a normal binary search. So we just set L and R to be 0 and N -1. Okay, so if that's not the case, then we have a more complicated situation. So we'll say otherwise if it's true that the target is at least nums at 0, so if it's at least the first value, and the target is actually at most the maximum value, so if it's less than or equal to nums at min I -1. Okay, so this is basically checking if it's in the left partition. If it is, then we want L and R to be, well, we want L to be 0, and we want R to be the maximum, which is min I -1, the index of the maximum. Otherwise, if that's not the case, it's got to be in the right partition, so we will set up our bounds so that L is going to be inclusive at the minimum index, and we want R to be up until the end of the array. Then from here, we're just going to write a traditional binary search, which is really nothing new here. While L is less than or equal to R, we need an equal sign here because we want to check if that value on L.
Given a string S and T, then the shortest substring of S such that the character in T, including duplicates, is present in the substring. If such a substring do not exist, return empty string. Okay, may assume the correct outputs always unique.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve minimum window substring. We're given 2 strings, S and T, and we want to return the minimum window in the string S, which contains every single character present in string T. And it's possible that that might not even exist, in which case we can return an empty string. So in this case, our string S is this big long string, and our string T is this A, B, and C. So we don't need to find A, B, C in here. We just need to find a substring of S that contains all these characters, and we want to find the minimum string that contains all these characters. So one possible string is this, right? It has A, B, O, B, E, C. So it has A, B, and C, but there happens to be a shorter string that has all of those as well. This string, B, A, and C. So they are out of order. So B, A, C, and there's an N in there as well, but this happens to be the shortest one. It's length 4, and so that's the result that we're going to output. So what's even a brute force way to solve this? So we're given S and T, right? And we want, like, if we're checking a substring, right, like this substring, maybe this is our solution, right? How do we even determine that? Well, let's use some hash maps. So these 2 are our hash maps. You can see I have 1 for T. What does this hash map represent? Well, you look at T, right? Because for each of these substrings, we just want to make sure that it has at least 1 A, right? 1 A has at least 1 B, and it has at least 1 C, because that's what we have over here. We just want to make sure
You're given a beginning of a linked list head and the integer n, and remove the nth node from the end of the list and return the beginning of the list. You're given the beginning of a linked list head and integer n. Remove nth node of the end of the list and returning the beginning of the list. So I need to take the 2 out, second thing out. Okay. So it's like 3 iterations, right? So what should I use for I in range, for I in n, range of n, how do I remove a linked list? Okay.
Hey everyone, welcome back. Let's write some more neat code today. Today let's solve remove nth node from the end of a list. So we're given a linked list, and all we need to do is remove the nth node from the end of the list, and then return the new list. So that's pretty straightforward, right? So in this case we got 5 nodes. We just want to remove the n equals 2, so meaning the second node from the end of the list, right? So this is the first from the end of the list, this is the second, so we remove this, and then we return this list, which now has 4 elements remaining. So what's the easiest way to solve this? Well, they say from the end of the list, that's inconvenient. If it was from the beginning of the list, it'd be super straightforward, right? N equals 2, remove this node. How can we make that even easier? I mean, what if these pointers were reversed? Can't we just reverse this linked list, start from here, and then remove the second node, and then we're done? That's definitely a possible solution, but it requires reversing the linked list, which we don't actually have to do, and I'm going to show you the easier way to do it. So let's say n equals 2 again, so we want to remove this node. So how can we identify that this is the second node from the end of the list? Like a lot of linked list questions, we can use 2 pointers, but how are we going to make use of our 2 pointers? So what if I had 2 pointers, right? A left pointer and a right pointer. The left pointer is at the beginning of the list, and the right pointer is shifted by n equals 2. So our right pointer is going to be shifted 1, and then it's going to be shifted again, and our right pointer is going to be over here. So now we're just going to keep shifting our pointers until this right pointer is at the end of the list. And watch what happens.
While R is true, I need to do punch him. I want to punch this motherfucker. So while R is true, I need to do something. While R is true, I need to go over. So for I, current, no. L next, L is equal to L dot next, R is equal to
right pointer is at the end of the list. And watch what happens when we do that. So we're just going to be shifting each pointer by 1, and this is going to make sure that the space between these pointers is exactly equal to n, which is 2, right? So now we're going to shift by 1 again, making sure that the gap between them is still 2. Now we're going to shift 1 last time, because right is almost at the end. So now our right pointer is at null, right? It's at the end of the list, it can't go any farther, and our left pointer is exactly at the node that we want to delete. And the reason is because, remember, the offset between these two is n, making sure that we have the node we want to delete. Now, there's only one problem. We have access to the node that we want to delete, but we want to delete it. How do we delete it? The only thing we have to do is take this pointer, cross it out, and then reassign it over here. We're at this common technique, insert at the beginning of this list that we don't really use. Instead, if a left pointer, update its pointer, and say return. And since this is a 2-pointer technique, the time complexity is going to be big O of 10. A is set to the head of the list because we're inserting it at the beginning. Next, we can initialize our left pointer to dummy, and we want our right pointer to be head plus 2, right? Or head plus n, whatever n happens to be. So we need a loop to do that, right? We can't just do that with a calculation. So we can initially say right is equal to head, the amount that we get. Update the left nodes.
It's probably like the easier medium question I would have to say. So we're going to add the list, and we want to remove the node from the end of the list, and as usual, we're turning the linked list head. So for example here, we're given a list of 1, 2, 3, 4, 5, and as you can see down here, n is equal to 2. So n equals 2 means 2 nodes from the end, so if n equals 1, that would be the end, but n equals 2 is the second node from the end here, that's down red here. It basically just means we don't want that node to be in the list. So we want 1, 2, 3, just as it was. We want to skip over that 4 and just go to the 5. Okay, and there might be actually some edge cases here where you have, say for example, just one node. Well, that's just going to be removing the head, so you want to actually return none because you wouldn't have the linked list at that point. And if I were them, I probably would have made another edge case where you had the same list but n equals 2, so that would be removing the head here because that would be the second node from the end is the head, and so you'd actually have to return just 2 instead because 2 would have to be your new head as well as the head. So suppose this is our first example, we're going to play around with it a little bit, and n is equal to 3. So that means you want to remove the 1, 2, third node from the end, so basically you want this 1 to just pass by that 2 and carry on over here. Now as with some other, the dummy and the head of the behind pointer. So we write, you might be wondering, well, why wouldn't we just return the head? Well, we'll see that in an edge remove here that's really just pointing the garbage at this time, and so now.
So once created, it remains same. That is the problem. Why fixed size is the problem? See, unless we are sure that we are going to store some number of elements, if we know the size, the number of elements, then we can create an array of that particular size. If we don't know how many elements we are going to store during the runtime of a program, then we cannot decide the size of an array. If we take some random size, then that size may be either insufficient or it may be excessive. For example, I'm not sure how many elements I'm going to store. So in the program, if I declare an array of the size 10, then in this array I cannot store more than 10 elements. Suppose I have more than 10 elements during runtime, then I cannot store them. And if I am just having 2, 3 elements, then a lot of space in that array will be wasted. So I take a larger size, 100. Now again, I cannot store the elements more than 100. So during runtime of a program, don't know how many elements will be required. See, one thing I'll make you clear. We are programmers. We write programs, applications. For whom? For users, people who use our programs. So people who use our programs will decide how many elements they are going to enter into the program. So there, what will be the list size or array size? We don't know. So at runtime, the list size will be decided. But at coding time or compile time, we have to give the size. This is the problem. So this is the problem with array. Then next, let us see the difference between array and linked list. So I'll discuss more about array, then I'll come to linked list. Now, little bit of revision. We already know that we can create an array either inside stack or we can create it inside T. So for creating an array inside stack, we say integer a size some size. I'm taking a small size here. So this array will be created inside activation record of main function. So array of size 5 will be created. Then if you want to create an array in heap, then you should take a pointer. So for pointer I'll take the variable name as p. Then you should say new whatever size you want. So this size can be taken at runtime and mentioned here. That's the benefit. But directly I'm writing it as an example. So pointer p will be available here, and an array of size 5 will be created inside p. This pointer will be pointing on it. So this is inside stack and this is inside p. But the benefit of an array is that all these locations will be contiguous. They will be side by side. So you can access them with index. That's the 0th element, first element, second, third, and fifth element. So randomly you can reach on any element. So array, imagine just like a bench. There's a bench of capacity size. 5 people can sit on that bench. So when you're making a bench, that time only decide what size you want, then that capacity is fixed. Now only goes into the bench. If more people, there's more space. If less people, then space is fixed. So this is like a bench. Now coming to linked list. Here what we want is, we don't want a fixed size bench like this array because we don't know the size. Who is using our program and what is his requirement, how many elements we don't know. Let him go on giving elements as many elements as we want. So let the user give as many elements as we want. Then we cannot go for an array. And one more thing, let the user add more elements and also remove elements. So we want some data structure which should grow and reduce in size. So we want a variable size data structure. So for that, I'll just share the idea about it. linked list. So for that, we must create memory in heap during runtime. And we should use linking.
Yup. How you doing? What have you? You're on a medium problem. True palindrome. Oh, group anagrams, yeah. Yeah, a lot of the hash map and hash table stuff still kind of like, I don't know, it's kind of easy and it's, I mean, easy and like difficult at the same time, you know what I mean? Your voice is kind of breaking. Can you hear me? Go on. Yeah, I can hear you, yeah. Yeah. Yeah, but like I think hash map is like used in every other data structure too. So when you like do medium problems with hash maps, it's like so like kind of specialized, and it's like you have to know the edge cases with like integers. I mean ASCII values and all of that bullshit, you know. But yeah, that's like such a specific edge case. You like never use it in like any other context using hash maps, and you couldn't even like remember it being like a rule that you can use to like other hash map solutions, you know what I mean? But it's just like one of those where you have to like just memorize it, you know what I mean? There's no other way. I mean, you can kind of understand what the ASCII value but it's like, yeah, the crazy thing is hash maps is used in like everywhere, like even like the math and geometry at the bottom. There's some hash map use cases, but it's not strictly like some ASCII value, like shit like that, you know what I mean? Have you done the easy ones on the top? Yeah. Hmm? 5. Yeah. Yeah, I did. I did like a linked list. Linked list is like I remember like doing linked list all the easies, and I try to like do another easy one which I've already done before. Like, bro, it was so fucking. It made no fucking sense. I don't know why. I remember doing it like a couple of months ago. Looking back at linked lists, I barely fucking understand it. It's crazy. Yeah, now I have like an idea back again, but yeah. You know what's the crazy thing? I think every thing here has like their own like little trees. You know what I mean? So linked list, you could do like three other ways, three different methods of completing a linked list solution. A trees has like binary search tree, breadth first search, depth first search, iterations. You know what I mean? So it's almost like just like it's better to like know those kind of methods rather than do like every single flowing cycle, dummy linked list, slow and fast linked list, shit like that. Slow and fast pointer. I guess I'm gonna do some linked list tomorrow. Get refamiliarized with all of that. Yeah, that's what I did. Yeah, I did every easy, and I went back and did the most, I mean, not like the most common, but the most whichever like kind of makes sense, like which progression kind of makes sense. You gotta like go with that. If the progression doesn't make sense, that you have to like, for example, the linked list mediums. I haven't done any mediums on linked list, and if I like try to do that now, I don't think I could able to do that, right? So like whichever mediums make sense, you gotta. Yeah. That's the thing. Like sometimes the mediums are like easy enough for you to like attempt it, but sometimes mediums are like borderline hard. You know what I mean? Like for example, the three-sum in two-pointers is like pretty difficult. You have to like look into like a lot of edge cases and stuff like that. What is it? Yeah. It is, yeah. Yep. What is it? So I did like a linked list problem, and I was doing a binary search problem. So I couldn't do the but both of them I couldn't like kind of do it. It's kind of difficult. I don't know. The linked list problem, I think I've like actually done it before, and it's kind of difficult. I was trying to like remember what I was doing, but the binary search, I got the intuition behind the binary search one, but yeah, I couldn't like make it work. I need to like look at the solution. So yeah, I'm thinking of doing linked list tomorrow. Are you gonna do some lead code after this, or? Are you gonna do it now, or after the call? Alright bro, I'll see you tomorrow. I think I'm done with it's first thing in the morning, done with lead code. Alright bro, see you tomorrow. Bye. So these what am I doing? you.